Bismillah ar-Rahman ar-Rahim. Now we were discussing the types of flow. So if the criteria is based on the flow depth with respect to time and space, we already studied that open channel flow, if time is the criteria, so if the depth is the variable that is to be considered, if the depth is not changing with respect to time, you can see here partial y by partial t is equal to 0, not changing with respect to time. So that is known as steady flow. And if the depth is changing with respect to time, that is known as unsteady flow. Now, unsteady flow problems are not included in your syllabus. So that's why our main focus is that on the steady flow problems. All the problems, whether uniform or non-uniform, so these are all steady flow problems. Means the depth is not changing with respect to time. Now when space is the criteria, so then in that case, if the depth is constant with respect to time, that is steady flow. But if the depth is constant with respect to x, that is known as uniform flow. It means that the depth is the same at all sections. Now strictly uniform flow is very difficult in nature, that the depth is the same at all sections. But anyhow, we make this assumption and we analyze and design the channels based on uniform flow equations such as the Manning's formula and the Chezy formula, and the results are satisfactory. Now we studied about the uniform flow, and in the last lecture we started with non-uniform flow, where the depth is changing with respect to x along the length of the channel. So that we commonly call as varied flow. Now because the depth is changing with respect to x, so that's why we relatively say that the changes can be gradual or can be abrupt. So if the changes in the depth occur gradually over larger distances, that is known as the gradually varied flow. And if the change in depth is gradual and over a short distance, that is known as rapidly varied flow problem. Now so far we have covered the uniform flow problems and the gradually varied flow problems. Next we will discuss the rapidly varied flow problems. Anyhow, in this unsteady flow can be uniform flow, means that the depth is changing with respect to time but it is constant along x. This is rare. It's very difficult to establish the flow which is unsteady and at the same time it is uniform flow. So we have unsteady flow and the depth is also changing along the distance, that is the varied flow. And also because the depth is changing, can be gradually varied flow and rapidly varied flow. But remember, unsteady flow problems, these are not included in your syllabus. So that's why our main focus is on steady flow problems, steady uniform flow, and steady non-uniform flow problems. Now, as we learned in the previous lecture also, that if the flow conditions do not change, the channel cross section remains the same, we expect that the uniform will continue to occur. But because we have obstructions in the form, like you see here, this is a gate structure that we need to operate to control the flow of water. Or we have other control structures, for example, we have a dam, a weir here, or also that the natural topography of the ground, that we have one slope that is meeting another slope. So then in that case, we cannot maintain the uniform flow throughout. So that's why the flow, depending on the flow conditions, can switch between the rapidly varied flow and gradually varied flow conditions. So that's why practically we encounter all these types depending on the given conditions. We have uniform flow. Accordingly, we studied how to analyze uniform flow problem. If we have gradually varied flow, then we just finish the problems that how we analyze the gradually varied flow problems. And now we will look that if we have rapidly varied flow conditions, how we will analyze those problems. Clear? So how to mathematically differentiate for the uniform flow, because the depth is constant with respect to x, so that's why this dy by dx, that is equal to 0. This dy by dx, it is the rate of change of depth along the length of the channel, which we assume as x. In the gradually varied flow, because the depth is changing gradually, so that's why it is found that this dy by dx is very small, less than 1. Clear? It is less than 1. And when we have rapidly varied flow, as the name indicates, it means that the change in depth will be abrupt and over a shorter distance. Clear? So in that case, you see that this dy by dx is approximately 1. So you can see here the rate of change of depth with respect to x is greater as compared to the gradually varied flow. Now, this rapidly varied flow occurs when a water flow depth changes abruptly over a very short distance. So these are relative definitions, that the flow depth will change abruptly and over a short distance. We will see that when we consider the short distance, what we mean by this. When we derive the equations that we will use to analyze the rapidly varied flow problems, you will see that what we mean by the short distance. Clear? Now, examples of rapidly varied flow include the weirs, as we studied weirs as measuring devices. So downstream of the weir, I will again show you that slide. You will see that rapidly varied flow occurs. We have flow control structures. For example, we studied about the Venturi flume, the partial flume, etc. Flow measuring devices, as already discussed. This flow control structures can be, for example, you saw here this gate structure also. And remember, this gate we can also use for measurement of discharge if it is properly calibrated. Then a very typical example is the hydraulic jump. This is what we are going to study in detail. Energy dissipations. Sometimes we have to dissipate the energy, such as in case of the hydraulic structures, to reduce the damaging effect of fast moving water. Flow over spillways, because when water flows over the spillway of the dam, the water flows with very high velocity. Clear? And after it flows the spillway, then the depth increases and the velocity reduces. So you can see that in that case, we can observe the rapidly varied flow. Transitions in channels. For example, we studied about the humps and the contractions earlier. Flow through non-prismatic channel sections, such as flow between the bridge pairs. So if we have the bridge pairs, you can see that the flow that is passing the bridge pair, so there will be abrupt changes in the flow conditions, and that will be, you can see here that the water flows, and in this section you can see that the turbulence which is created in this flowing water, so there is abrupt change in the flow depth. Similarly, you can see that this is a bridge, and through this bridge the water is flowing, and we have the bridge piers that we just discussed. So you can see here that there is abrupt change in the water depth, and the conditions can be that for corresponding to a rapidly varied flow. So how we analyze these problems? This is what we have so many problems. You can see here, these are all examples of rapidly varied flow. But remember, the main focus of rapidly varied flow will be the hydraulic jump. This is what we are going to study in detail, and that's why in your textbook you will not find the title rapidly varied flow. They just directly start with the hydraulic jump. So it means that it is a typical example of the rapidly varied flow problem. This we are going to study in detail. But we can have analysis of all these types of rapidly varied flow problems. Now to continue with this hydraulic jump, you see that this is the flume in the laboratory, the open channel where the water flows. So a hydraulic jump, which is a typical example of the rapidly varied flow that is observed here. This is the hydraulic structure. This is a broad crusted weir over which we establish YC so that we can measure it as a device, flow measuring device. But you can see that downstream of the weir, and we solved a problem on this, we have supercritical depth, and then this supercritical depth changes to subcritical depth here. But the transition from supercritical depth to subcritical depth cannot be smooth. The reason is that if you remember from the, let me take this example here, we have this supercritical depth here, and if this is going to change to subcritical depth, this is, let's say, the subcritical depth, this is the channel bottom. Now we can assume that, you see, this can be the case that, okay, this is now the water surface and the profile is here smoothly joining this, water becomes the subcritical depth, water flows. So what we are assuming here that this can be a smooth. Now this is not possible. This cannot possible. Whenever the depth changes from supercritical to subcritical, we cannot have a smooth transition, that the water surface will be very smooth and the water depth becomes the subcritical. This is not possible. So what we have is, what is the reason? The reason is that if we have this channel and this hydraulic jump, if you have studied the gradually varied profile, you will observe for some cases we observe the break in the water surface, which is known as hydraulic jump. So if we have this supercritical depth and it is going to meet the subcritical depth here, then smooth transition is not possible. It means that the water will break. Water will break and turbulence will be created, and after this turbulence, then the water can flow with subcritical depth. So why we have this turbulence? The reason is that if you remember, we studied that when we have, let's say this is the situation, and if you remember the M2 profile, let me take the M2 profile, it was a drawdown profile. So when it comes here, it becomes dash dash line. So at this point here, because this is the critical depth YC, at critical depth we studied that dy by dx, this was equal to what? The dynamic or the differential equation that we discussed. This is known as S0 minus S divided by 1 minus f square, where f is the Froude number. So now when the depth approaches here, what will be the Froude number for critical depth? The Froude number is equal to 1. So when it is 1, 1 square is 1, 1 minus 1 is 0, and anything divided by 0, what will happen is that this dy by dx becomes infinity. It means that this will be equal to infinity. And when we have infinity, it means that the slope is vertical. So when the water passes through the critical depth, here the slope will be strictly vertical. The slope will be strictly vertical. So because here the water, it passes through the critical depth, which will be in between the subcritical and the supercritical. This is the supercritical, the downstream that is subcritical. It means that we have a critical depth here. So when the water passes through this critical depth, the slope must be vertical, which the theory says. So that's why there will be a jump. There will be a jump, and that is universally known as hydraulic jump. This is what we call as the hydraulic jump. So it means that whenever the flow changes from supercritical to subcritical, it must pass through the critical depth, in which case the hydraulic jump will occur. So you can see here in this case that we observe downstream here, the flow changes to subcritical. Because it passes through the critical depth, you can see the turbulence, the break in the water surface, which is created. This is known as the hydraulic jump. This is universally known as hydraulic jump. There is no other name for this. Everyone knows that this is hydraulic jump. That's why it is written in your textbook, universally known as hydraulic jump. And it is the typical example of the rapidly varied flow. So now that in this case you see here, just like in this case also, this is the hydraulic jump. So that's why in this area we cannot apply the gradually varied flow theory. The gradually varied flow theory becomes invalid. Why? Because this is no longer a gradually varied flow. This becomes a rapidly varied flow. So that's why we have to develop other equations to analyze these type of flow problems. So this is a typical example. You can see here in the lab that we can observe this hydraulic jump. This is one way of creating hydraulic jump. There can be different ways of creating the hydraulic jump, but this is one of the example that you can see here, the hydraulic jump that is created in the lab with the help of this weir, broad crusted weir. Now to continue with this, you can see that a hydraulic jump that is downstream of a sluice gate. So in this case, you see the turbulence in the water, and because the depth changes under the gate, the depth is supercritical. It is like this. This we already studied. Even if we have mild slope, we can create the supercritical depth because we force the water to be supercritical. If you remember, this was the example given for the M3 profile. If you study the water surface profile examples, which we studied in the previous lecture. So you see we have subcritical flow, but the gate is forcing the flow to be supercritical. So that's why, because we have the slope is the mild slope, if you remember from the previous lecture, on the mild slope we are forcing the flow to be supercritical, means that the depth is less than YC. So as the water flows, what will happen? Because we have mild slope and it cannot sustain the supercritical depth. So that's why the depth will try to go to the subcritical depth. And because this is supercritical depth and downstream it is trying to achieve the subcritical depth. Because we have mild slope, that's why this supercritical depth here, it will pass through the critical depth. So in here it has to pass through the critical depth. This is, let's say for example, the critical depth. So because it passes through the critical depth, that's why there will be a break in the water surface, and after the turbulence, then the water can become subcritical and it can continue to flow. And that's why as a result of this was classified as M3 profile on a mild slope, but in the zone 2, because here the depth, it is below Y0 and it is below YC. So a rising profile, increasing profile, and this was classified as M3 profile. You can check the previous lecture. So you can see here, this is a control structure, because by operation of this gate, we can allow the desired discharge in this canal here. This is called a sluice gate. So you can see here, this is kind of an example of this explanation why a hydraulic jump occurs downstream of this gate. So these type of structures you will study in detail when you study another course, that is irrigation engineering. Clear? Now, to continue with this, another example of hydraulic jump, that is our main focus in rapidly varied flow problems, at the toe of spillway. Now you can see here that when the water flows over this spillway, it's very fast. The depth is very small and the velocity is large. So that's why this, if we do not have a hydraulic jump, this is hydraulic jump. You see this turbulence which is created here, this is known as hydraulic jump. Now, if we do not have this turbulence, what will happen? This very fast moving water, it will pose damage to the channel downstream. This is what I am saying here. If I can make a figure of this again to explain what this is, let's say we have a dam, and now over this dam the water flows. So now this water is coming with very high velocity, and if this downstream of the dam or the channel, you see this water, it is striking this ground very fast. So what will happen is that if there is no protection, with the passage of time, it will remove the material from here. So this channel bottom will go down and down. You see here, scouring will take place. So the channel bottom will become like this, because this very high velocity is coming and it is striking. So when this bed of the channel, it is, you see here that scouring takes place, this will ultimately pose threat to the foundation and stability of this hydraulic structure, because you are removing the material, you study geotechnical engineering due to seepage. So it will pose damage to the stability of this hydraulic structure. So that's why, to protect the hydraulic structure, this ultimately it will pose threat to the hydraulic structure. First, the material will be removed from here, but then ultimately it will pose threat to the stability of this structure. So that's why what we do is that it is desirable to have this hydraulic jump. Because of hydraulic jump, there is loss of energy. So the destructive energy, greater portion is lost. And after the hydraulic jump, what will happen when we have this hydraulic jump? After the hydraulic jump, the water flows with greater depth and less velocity. So this is actually desirable in case of hydraulic structure, downstream of hydraulic structures, because it dissipates this energy of fast moving water here. You can see very fast moving water, it will damage the bed of the channel, and ultimately it will pose threat to the structure itself. So that's why, remember, this hydraulic jump is desirable, so that the destructive energy is dissipated, and after the hydraulic jump, the water flows with less velocity and greater depth. So the danger is reduced. Now you can say that on one side, this hydraulic jump, it results into dissipation of the destructive energy, but itself it is huge turbulence. Itself it is huge turbulence. So that's why on one side the hydraulic jump, it helps in dissipation of the energy, loss of the energy. But on the other side, it can also be dangerous. So there are two sides of a hydraulic jump. On one side, it is desirable to dissipate the destructive energy to protect the downstream side of this hydraulic structure, the channel bed, and also ultimately it should not endanger the stability of the hydraulic structure. But on the other side, there is also turbulence. So that's why, to protect against the damage from this hydraulic jump, what we have to do is that we have to provide protection downstream of the dam. So what we do is that at downstream end here, we have to provide protection so that the hydraulic jump occurs, the downstream of the, or you can say bed of the channel, is protected, and ultimately the stability is ensured. But this hydraulic jump should contain in this protection to avoid any problem from the hydraulic jump because of this huge turbulence. So what protection we provide here, this we are going to learn by end of this topic. So what type of protection we provide here, this we are going to learn later on when we finish this topic. So you can see here that this hydraulic jump, it is desirable. We will see what are the uses of hydraulic jump. So because we encounter this hydraulic jump, that's why we need to, because in the design of this protection, you must have the analysis of the hydraulic jump. And then we have to determine that because of the hydraulic jump, how much energy will be dissipated. So accordingly, we can design the protection that is provided downstream. It's very important topic. But because this course is very elementary, very basic, so we will just study for understanding purposes. I will try to explain the content as per the time availability. Now, this rapidly varied flow, also known as local phenomena. This rapidly varied flow is in open channel hydraulics. It is also known as local phenomena. Now, the hydraulic drop and the hydraulic jump are typical examples of the local phenomena, means the rapidly varied flow. These two are the typical examples that are commonly explained in open channel hydraulic books, beside the others. So a free overfall, which you can see here, this is an example, a free overfall. So the free overfall is an example of hydraulic drop. So we can study the hydraulics of this drop structure. And we have this hydraulic jump. So you can see here the water here flows with very fast velocity and shallow depth, supercritical depth, and when it changes to subcritical depth here, smooth transition is not possible because the water has to pass through the critical depth. That's why you can see that there is a huge turbulence created that is known as hydraulic jump. This is hydraulic jump. So these are the two typical examples that in open channel hydraulics that we need to discuss when we study the rapidly varied flow, but there are many examples of rapidly varied flow. Now, this hydraulic drop, which is a typical example of the rapidly varied flow problem, this I just briefly explain here in this slide, because this hydraulic drop analysis is not given in your textbook. And I said that I will try not to go beyond the textbook. but just very briefly I try to explain it here for your understanding, but our main focus will be that on the hydraulic jump. Now you can see here that we have a hydraulic drop. This is a drop structure that we provide. Because why we need to provide this drop structure? Because sometimes the natural topography, natural surface of the ground, it does not continue with the same slope. So time and again, if two different slopes meet each other, then we have to provide these type of structures. So this you will study in detail in the course irrigation engineering. Clear? Now in here, you see that because of the drop structure, the water surface has a curvature. And we have a drawdown curve. This is a decreasing profile. For this curve, dy by dx is negative, a drawdown curve, as we already studied. Now for this curve, if you calculate dy by dx, it will be negative. So this type of curve, we call them drawdown curve. We just solved a problem also. Now in this case, you can see that because of the overfall, this is the actual water surface that occurs. This is the solid line. Actually, theoretical water surface, assuming parallel flow, should follow this line here, this dash line here. As I already explained before, that if we assume the parallel flow assumption that we make, clear? So then according to that, the surface should follow along this dash line here, this one. Why it should be decreasing? Because of the friction, there is always a loss of energy. So the energy always decreasing in the direction of flow. This is the same in the pipe flow as well as in open channel flow. So there is a deviation from this theoretical profile. Why? Because we have curvature. It's no longer assuming parallel flow assumption. So that's why you see here that the actual water surface is below. And we have, this is subcritical flow. Why? Because in here the depth is above the critical depth. This is your critical depth and the depth here is above. So we have subcritical flow, but because now a drawdown curve, so in here it passes through the critical depth. And this is what we studied as a control structure, if you remember. So this critical depth occurs experimentally. It has been found that this is 3 to 4 times the YC. And the depth is below at the brink. At the brink of this drop, the depth is below YC. Because normally we assume the YC to occur here. But instead of here, this we already discussed in the previous lecture, it occurs upstream at a distance 3 times 3 to 4 YC. Now in this case, if you draw the specific energy curve for this, Y is equal, Y versus this E, depth versus the specific energy. So you can see that we have the depth here, which is represented by this point P. And now because of the drop structure, the drawdown curve, the depth is decreasing. So what happened? It comes at this point to YC. And then even coming below, because this Y naught is here a supercritical depth. So this depth is coming here, and at point C, we have the critical depth. And we already know that corresponding to the critical depth, we have the minimum specific energy. And as a result of this, there is a loss of energy, which we can clearly see even from the diagram. So this delta E is the loss of specific energy. Now, this type of example you already saw also in gradually varied flow. So you can ask a question that is this an example of gradually varied flow problem or rapidly varied flow problem? So the thing here is that this dy by dx, depending on the flow conditions, if this drawdown curve that we see here, if it is very, very small, means very, very small, less than 1, then we will classify this as an example of gradually varied flow. But if this change in depth is more, then this is an example of hydraulic drop, and this is an example of the rapidly varied flow problem. Then we can classify this as rapidly varied flow problem. So I'm not going into detail of this analysis of the hydraulic or drop structures, since this is not given in your textbook. So that's why our main focus will be that on hydraulic jump. Now, this hydraulic jump, it occurs when supercritical flow changes suddenly to subcritical flow within a short distance. This is the comprehensive definition of that hydraulic jump must always occur whenever the flow changes from supercritical to subcritical, because it has to pass through the critical depth, so smooth transition is not possible. It is used for dissipation of energy, as I already explained, in flow to protect dams, weirs, and other hydraulic structures. Why? Because the reason was that the water passing through the hydraulic structure, as I show you in the picture, for a spillway and the sluice gate structure, the water flows with very high velocity. So that's why the hydraulic jump is desirable in these hydraulic structures for dissipation of the energy. And how much energy dissipated, that we will develop an equation to calculate that. So you can see that when we have the supercritical depth, and when the depth changes from supercritical to subcritical depth, so because it passes through the critical depth, that's why the smooth transition is not possible. We will have this turbulence, and this is universally known as hydraulic jump. Clear? So how to analyze these problems? So we will develop equations just like we develop the theory for gradually varied flow. We will develop equations how to analyze the hydraulic jump. By analysis, we will mean that what is the depth. For example, what is the depth upstream of the jump? What is the depth downstream of the jump? How much is the energy dissipated as a result of this hydraulic jump? What is the length of this hydraulic jump? So these are the questions that we would like to answer. Clear? Now in this case, you can see that the water flows over this weir. This is a model study. Here we show a weir, a raised structure over which the water flows. So now in this case, you see we have subcritical flow, then we have critical flow, then we have, you can see here that we have supercritical depth, and when it changes to the subcritical depth here, you see here it passes through the critical depth. So this is known as hydraulic jump. This is hydraulic jump. Smooth transition is not possible. Now this smooth transition, before I try to explain, let us see one or two videos on this. You can see here that even in the washroom sink, we can create this circular jump. You see the water which is coming from the tap, the depth is shallow, and then it passes through this turbulence, and the depth after the turbulence is more. So this is actually a hydraulic jump. Whenever the flow changes from supercritical depth to subcritical depth, this hydraulic jump will occur. Clear? This is another example of the hydraulic jump. You can see here the water changes from supercritical depth to subcritical depth. This is hydraulic jump. You see the surface cannot be smooth. This is another hydraulic jump. So there are different types of jump that we will study. Now this is an example where you can see here downstream of a sluice gate. You can see here that the depth changes from supercritical to subcritical. This hydraulic jump will be formed. So here the depths that are denoted by D, and these equations we will study how to analyze these types of problems. Clear? You can see the head loss as a result of this hydraulic jump. So now you can see here that this hydraulic jump which occurs whenever the flow changes from supercritical to subcritical, so there is loss of energy. Now in this equation you can see that if we draw the specific energy, we have this as the depth of flow, and in here we have the specific energy. Now we draw the specific energy curve. You can see here that for this y1, which is the depth before the jump, because in here where is the depth? We cannot take the depth here. So that's why this is the depth that we can consider the supercritical depth. Here where is the depth? So that's why it's turbulence here. And after the turbulence we have the subcritical depth, which is here y2. Now in this case we are here in this point along the specific energy curve. We are here, and in the next point here, this is the depth at this point here. This is the depth at this point here. Now you see that this y1 and y2 are not for the same specific energy. If you remember last time, it was for the same specific energy. Clear? So these were called alternate depths. Now these are not alternate depths. Why? Because they are not for the same specific energy. If this y2 was here, then it can be the alternate depth. Because they are not. These are not for the same specific energy. That's why these are not alternate depths. So we cannot calculate this y2 from this specific energy alone. That is now the problem. Why we cannot calculate this y2 now from this specific energy alone? Because this delta E, which is the loss of energy, because you see we move from here. This point is here. So there was a loss of energy. There is loss of energy. But this energy is unknown. How much energy is lost? We don't know. So that's why to do the analysis of the hydraulic jump, if y1 is known, let's say here the depth is known, what will be the depth after the jump? This we cannot calculate alone from the specific energy diagram. What is the reason? Because the reason is the loss of energy is also unknown. If we know how much energy is lost, then we can plot this vertical line and we can determine this y2. So you can see here that there was a jump from this smaller depth to this larger depth, subcritical depth. This is the hydraulic jump. So Alone, this specific energy curve is not sufficient to calculate what is this Y2. Why? Because delta E is also unknown. So that's why we need an additional equation or additional figure that will help us to determine what is the value of Y2. That is what we are going to learn in this topic. Now this is the figure which is given in your textbook. So you can see here that we have supercritical depth, and when it changes to subcritical depth here, so it passes through, this is known as the hydraulic jump, a turbulence which is created, a break in the water surface. We do not have the smooth line. So that's why it is no longer a gradually varied flow problem. That's why this is a typical example of the rapidly varied flow problem. Now, you can see here that we have this Y1, which is the depth upstream, that is the supercritical flow. And we have Y2 downstream of the jump, that is the subcritical flow. And you see here that for the supercritical depth Y1, we have E1 here, and then there is a loss of energy, as we are saying, as a result of this hydraulic jump. So the energy is reduced to E2, and in here we have this depth Y2. You can see here there is a jump from 1 to 2. That is the hydraulic jump. So this Y2 we cannot calculate alone from the specific energy because this delta E is also unknown. We need additional information, additional equation to solve. So I will just explain these characteristics, then I will stop the lecture here. We will continue with this in the next lecture. The following are the characteristic features of rapidly varied flow. This is from Open Channel Hydraulics by Venti Chow. Now in this case, what are the characteristics of rapidly varied flow? Curvature of the flow is pronounced so that pressure distribution cannot be assumed to be hydrostatic. What it says here? It says that at this point here, this is the channel bottom here, and we have supercritical, and then we have subcritical depth. And in here we have this turbulence of hydraulic jump. So it says that in here the curvature is so pronounced that the pressure distribution cannot be assumed to be hydrostatic. So it means that in here you can draw a pressure distribution diagram here. For example, we can draw here the pressure distribution diagram, hydrostatic due to the depth. So we say that, okay, this is the hydrostatic pressure distribution diagram. After the jump we can draw, because we have subcritical flow. So this is the hydrostatic pressure distribution diagram. Clear? But in here, for example, here you cannot draw. This is not possible. Curvature is so pronounced that this assumption of hydrostatic pressure distribution diagram is no longer valid. This is fine just before the jump, and after the jump is possible. But in here, the assumption is not valid. The reason is curvature of the flow is pronounced so that pressure distribution cannot be assumed to be hydrostatic. The second characteristic is that the rapid variation occurs over a relatively short distance so that boundary friction is comparatively small and usually insignificant. Now it says that this hydraulic jump which occurs here, you can see this hydraulic jump which occurs, it is on a relatively short distance. This distance here, let's say this is the hydraulic jump. So it says that this distance, this is very short. This is short distance. Since this is short distance, so when we do the analysis, we can neglect the friction here. This distance is very small. So we can neglect the friction in the analysis. We will derive the equations in case of this hydraulic jump. So what we will do is that we will neglect the friction forces in the theory, and it will not greatly affect the results because hydraulic jump has been studied experimentally. So we will neglect the friction because this distance is very small. So we can neglect the friction forces without introducing much error. So that's why it says that the rapid variation occurs over a relatively short distance, so that the boundary friction is comparatively small and usually insignificant. So we neglected in the analysis without introducing much error. The rapid changes of water area occur in rapidly varied flow, causing the velocity distribution coefficients alpha and beta to be much greater than 1. Now you can see here that this alpha, which is the kinetic energy correction factor, at the two sections that we consider. So in here we will have this alpha, let me write down first alpha, then I will come to beta. So we have this alpha, which is the kinetic energy correction factor, and at section 1, and the kinetic energy correction factor at section 2. So far in the analysis we assume it to be unity 1, and this is we also did in case of pipe flows. In chapter 8 throughout we assume alpha 1 alpha 2 equal to 1. So far in this chapter we are discussing the problems based on the assumption that this kinetic energy correction factor, that is equal to 1. Why this is not equal to 1? Because the reason is we do not have uniform distribution of velocity, that we already discussed in the first few lectures, the velocity distribution in open channel flow. Because we have non-uniform distribution, that's why this alpha and beta needs to be written. Clear? That this is what we write down with this, the velocity head, alpha v square divided by 2g, the kinetic energy correction factor. Clear? So you already solved the problem on this in your midterm exam. We are so far assuming this to be unity. Similarly, we have this beta, that is the momentum correction factor. This is beta 1, the momentum correction factor. Beta 1 is equal to beta 2, and that is assumed as equal to 1. This is the momentum correction factor. As I told you, when we calculate the forces, so we already studied in fluid mechanics 2, summation of force is equal to rho q delta v. Rho q delta v. Clear? So in this case, you have to multiply this with beta, because this is the momentum, rate of change of momentum. So you have to multiply beta for correction because of the non-uniform distribution of the velocity that you consider here. Clear? So in that case, we have beta 1 and beta 2. Now in this case, you see that in this case, this variation is huge here in case of this hydraulic jump. So that's why this is characteristic of the rapidly varied flow, characteristic features of rapidly varied flow, that in case we have rapid changes of water area that occur in rapidly varied flow, causing the velocity distribution coefficients alpha and beta to be much greater than 1. So it means that in this case, we cannot assume them to be equal to 1. If you make this assumption, then it will affect the results. So that's why we cannot hold these assumptions anymore when we discuss the rapidly varied flow problems. Clear? So we will continue with this theory. In the next lecture, we will develop the equations, how to analyze the rapidly varied flow problems.